let's discuss linear transforms in this lecture. So yeah, this is actually the basic idea of one of the very basic ideas of linear algebra. So how do you view uh, matrix in general is it's like a transformation which takes a vector in one vector space, applies a linear transform over it, and takes it to another vector space. Okay, this is a general idea in linear transforms. We're going to look at it in a more systematic way. Okay. Say we have vector fields U and vector spaces U and V over a field F. Or a field F. Then the function which is defined from U to V is said to be a linear map. Is said to be a linear map if f of U1 plus U2 is equal to f of U1 plus f of U2 for all U1 comma U2 belong to vector space U. This is the first condition. The second condition is f of lambda U is equal to lambda times f of U, where lambda belongs to the field and U belongs to the vector space. So let's look at it in a bit more detail to understand what it is. So what does the first thing mean? You have two functions. Sorry, you have a function which maps. Okay, let's look at this in more detail. The first point. So you have a vector U1 and it is getting transformed to some V1 and you're applying this function over it. Okay, which is basically f of U1. So we have another vector U2. You're applying the same function over it and you get a V2. V2. So what does it say? So suppose you add these two vectors together, U1 and U2, and give it to the same function, U2. So ideally, what you should be knowing what U1 and U2 is, right? To find f of U1 plus U2. You should be knowing U1 plus U2. You have to compute U1 plus U2, and you give it to the function and get U1 plus U2. That is one way of doing it. But since it's a linear transform, what we can do is we need not actually have U1 plus U2. If you want to find just U1 plus U2, f of U1 plus U2, if you know f of U1 and f of U2, you basically just have to add them together. U1 plus f of U2 will give you f of U1 plus U2. Second thing is also similar. We have a U, we apply the transformation over it, and we got V, and we're scaling the U, the vector U by some factor lambda. So if we know lambda U, you just know the scaling factor. You just don't have to compute and give that again as input to the function. Basically, what you have to do is, if you know this, if you know U as V as f of U, so basically what you have to do is to find f of lambda U, you basically have to scale f of U. Or this is basically equal to lambda times V. Such transformations can be called as a linear transform. So you have to be always careful. There are many transformations which are not linear transformations. Any transformation, in fact, there are a whole lot of transformations which doesn't satisfy this condition. But whenever you are you're sticking to the space of linear transforms, this is what it takes. I mean, this is what is a specific peculiarity of such transforms. Is there a geometric interpretation to it? How do you look at this? Uh, uh, what things will be preserved whenever you're applying a linear transformation? Is it the lengths which are going to be preserved, or the length of the vector, is it going to be preserved, or is it the what do you call, the angles between the vectors which are going to be preserved? This is an interesting question to ask. Okay, maybe we'll cover it somewhere later in this course. So the questions to ask, some of the key questions. What all properties are preserved after linear transformations? Okay. So here by properties, what I mean is like length, vectors, or angles between vectors. Are such things preserved? There's one thing to ask. Another question is, if they're varying, how are they varying? What is the change? These are some good questions to ask whenever we are in the setting of linear transformations. Okay, let's move on. I think we'll discuss this over the course. Yes. Then let's look at some more important consequences. One of the first things to notice is the values taken by f on some basis of u completely defines f. What does this mean? Okay. This is actually something which is very useful when we're using a change of traces. Yes, suppose we have, I think the idea here is, if we have a set of, okay, I think we can discuss this in detail as per other subsequent steps. Okay, maybe we can discuss it now itself. So what we're trying to mean here is, say, let the vector space U, to denote the vector space U, has basis U1, U2, etc., UN. Remember, this basis is not unique. For a given basis, linear combinations are unique, but vector space may have multiple bases. It's not unique. And we have the linear transformations U1, the f of U, I mean V1 is equal to f of U1, V2 is equal to f of U2, etc. And Vn is equal to f of Un. Okay. Then any U belongs to this vector space can be written as a linear combination of the basis vectors. U is equal to alpha 1 U1 plus alpha 2 U2 plus alpha in U. Why is it so? Because alpha, it is a basis. Basis is ultimately a spanning set. Whenever you have a spanning set, you can write any vector as a linear combination of those vectors. Okay. So But we have already defined a transformation from U to V is a linear transform. Okay? By linearity, f of u is f of alpha u1 plus alpha to u2. It's alpha 1, sorry. Alpha 1 u1, alpha to u2 plus etc. Alpha in un, which indeed, by using this property, if you are giving a scale input to a particular function, you basically have to scale the output. And if you're giving a sum to the input, if it's a linear transformation, just have to basically take the sum of the outputs. So using that, the linearity property, what we can do is we can put this as alpha 1 f of u1 plus alpha 2 f of u2 plus etc. plus alpha n f of u. My bad. What is happening here? Yeah, alpha n un. But what is f of u? F of u1, this is v1. Alpha 2 is f of u2 is v2 plus etc. plus alpha n vn. So what does this mean? See, these coefficients, let's say we have u, which is actually f of u. So if I have u in a vector space V and we're taking a linear transformation on that, taking it to another vector space V, where we belong, we have, applying transformation on vector u and taking it to a vector space V, what in fact happens is, in fact happens is, if we've already expressed this u as a linear combination of a particular basis, what you have to basically do is apply the transformation on these basis vectors and take the same linear combination and add them together. So basically, you don't have to apply it over. So yeah, you can actually do a change of basis and find a new vector in this new vector space. That's a key idea here. In fact, it just determines. It's completely dependent on f, which is applied over the basis un. Hope that makes it clear. What I'm trying to say is, let's say we have the canonical space ijk. How do you represent ijk? We have vectors in, okay, let's take 2D, for example. We have the canonical vectors 1, 0, 0, 1. These are the, let's take this as the basis. And so we have, let's take this as u1 or e1 is more standard way to representing this, e1 and e2. Let's say our vector u is 2 times e1 plus 3 times e2. We applying some kind of transformation, f of u. Okay, so when we f of u, how do you find this? F of u, you can just retain these coefficients, and basically you have to apply these transformations on canonical vectors. As 3 times f of e2. You'll end up getting the resultant vector. No, you're trying to change the basis. So what does the change of basis do? It takes you from one space to another space. And suppose we had a vector here. Okay, let's try to draw it and make the idea a bit more clearer. Yeah, we are in a 2D space here. We want to do some kind of a mapping, which takes it to another space, another 2D space. So we had a vector already here. some random vector. It got transformed to some other vector. Here, this is the initial vector. It got transformed into this. How do you find this new vector? This old, new after transformation. How do you find this? You basically have to, these are the canonical vectors, right? Basically, I have to take the transformation of these canonical vectors, and we already know how this vector was really expressed in terms of these two vectors. Okay, may say that this is not accurate in terms of representation because vectors normally we represent uh, their tail to be at the origin. I'm sorry, yeah, whatever. One of the ends is at the origin, right? But it can be translated. Vectors doesn't have, if you don't fix an origin also, okay. Is that a vector space? Is another question. Okay. Very accurate way of describing, but I think it's enough to understand this concept. Okay, so basically what you do is you have to just transform these vectors, even in E2, got transformed to some other, let's say E prime, E1 prime and E2 prime. That is enough. Then you can use the same set of coefficients, which were the scaling factors for each basis, and you end up getting the new vector. Okay, that's the idea here. And let's look at a few more consequences. Zero vector always maps to zero. Why is it so? Because of the scaling property, right? Whenever we are, it's because of just the second property. I have lambda times a vector. U is after the transformation. Lambda times f of u. Good question. I should zero map to zero. F of u. Is it a consequence or is it is it a way of defining linear transformations? Do we always have to say that zero always map to zero? What do you mean by zero always map to zero? The input is zero, and f of u also will be zero. That's transformation for linear transformations. What will happen if it's not zero? How do you prove this? Can you prove this? Can we prove this? What are the cases where zero does not map to zero? And if you just do any kind of scaling, now zero always maps to zero, right? Right. See, if it's any kind of scaling, because multiplication with zero always ends up giving you zero. The only possible case is you can do a translation, right? Yes. Okay. How do you have a translation function? We have f of u could be some u plus some c, right? Here the scale doesn't matter because we're just looking at the zero vector case. We're trying to prove it. So let's say this is a transformation u plus c. So we're just taking the function and applying some translation on it. Yeah. Translation, does it have to be okay? Okay, let's take c is also a vector. Okay, more accurate. This is the translation. Okay. This is a constant vector, which we are always translating. Then f of u1, let's take this property, f of lambda times u1 is equal to, yeah, lambda u plus c. But if it has to be a linear transformation, f of lambda u has to be lambda times f of u, which in fact is lambda times u plus c, which is lambda u plus lambda c. These are not equal. So what does that mean? If you have a translation, it is not. I mean, translation by a concept. We have shift by a particular concept. It's not linear transform. Interesting, right? So this is not a linear transform. If it has to be linear transform, C has to be 0 for it to be a linear map. In fact, if that is 0, then 0 always maps to 0. I hope the argument is clear. 0 should always map to 0. Okay, let's look at a few more things. Any A belongs to Rm cross n. What is it? This is a matrix. It's a linear transformation. From Rn space to Rm space. And any linear transformation can be expressed as a matrix. Any linear transformation from Rn can be expressed as a matrix multiplication. This is another way of looking at matrix multiplication. We have always looked at a matrix like rectangular array of numbers. Another way to look at a matrix is, suppose we have to do a linear transformation on a set of vectors, let's say a basis or a single vector. How do we how do we represent that? Right? So what we can do is this is a matrix multiplication corresponds to a composition of linear transform. Is it a composition? Composition means it has to be some function within another function. Is it stacking or composition? Let's look at something. So let's say we have a vector v1, v2. Okay, let's take a very basic case, 2D case, v1, v2. And we have to apply linear transformation, right? Let's say we have to do simple linear transformation. Let's have to just do basic scaling of these vectors. So we need to apply an f of, let's take u1 and v2. Need to apply this transformation and make it lambda 1 u1 plus lambda 2 u2. How do we do this? This is not a dot product, mind you. How do you put the matrices? So basically, you have to scale this by this. Okay, how do we write this? How do we write? One way of writing this is, yeah, what I can think of is lambda 1, lambda 2, 0, 0, u1, u2. right? This is how we get this. And this is a basic 2x2 matrix. This is how we write this transformation. What will happen if we have to add more transformations to it? Let's say we have to take another transformation. Mu1, mu or yeah, these are just lambda 1, lambda 2. Let's say we are applying another scaling on top of it, like C1. So let's take it as mu1, mu1, mu2. What is the product of these two matrices? We have u1 times lambda 1, lambda 1 plus 0 times this mu1 lambda 1, 0 times this, 0 times that, 0, 0 times this, 0 times this and this, 0, mu1 lambda 1, u1, u2. So what we've done is we have actually put two matrices back to back. Ultimately, this matrix can be viewed as a composition of these two matrices or a function on top of another, right? Composition of these two functions. So matrix multiplication can correspond to a composition of linear transforms. And another important question is what if this value is not 0? Mu1, 0. Let's say we have another A here, B, lambda 2. And if you apply, we do this matrix multiplication to this particular vector. What are the resultant vectors? Lambda 1, A1 plus lambda 2, sorry, lambda 1, U1 plus A times U2, B times U2 plus B times U1 plus lambda 2 times U2. What does these do? Rather than just, there is some kind of a cross connection, right? Here we're just using a scaling which was dependent only on U1. But here, along with U1, the vector got transformed to, it got scaled by lambda 1 times that particular vector. Along with it, we have actually added a scaled version of U2 component of that vector also to it. Now, this is how matrices, a proper, so early cases we are considering only the diagonal matrix, but we have full matrix, full in this sense, I would say. It's not a diagonal, it's not a special matrix like a Neper-triangular matrix or a diagonal matrix or identity matrix or anything like that. We have a general matrix. Then we can actually take the linear combination, scale them with multiple scaling factors, add the components in between in some scaled fashion, and add them together. So this is what matrix multiplications basically does. Takes one of the components of U, it basically takes, so you have to just see how a particular component is weighting. You basically have to take up that component, scale it by some factor, scale the second component by factor, and add it to the first component, and then getting the first component of the matrix. This is how matrices actually performs a linear transform composition over the vectors. So matrix multiplication can be also viewed as linear composition, a linear transform. This is also another way of looking at matrix multiplication. Okay. So we'll wrap up this lecture now. Uh, yes.